Trend analysis. We are going to discuss trend analysis, and for that purpose we're going to cover the following topics: definition of data series, distinction between signal and noise, definition and application of least squares approximation, definition application of least squares interpolation, and the statistical aspects of least squares approximation and interpolation. Our discussion on trend analysis will be decomposed into shorter video lectures. At the end of the whole session, the students should be able to summarize the characteristics of interpolation and approximation, apply interpolation and approximation techniques to various situations in geomatics, and to assess the quality of approximation fitting using statistical tools. Why do we do trend analysis? Sometimes when we are dealing with a data series, we may want to learn about the trend of this data series. And what is a data series? A data series is a set of repeated observations of the same quantity, either in time or in space. Examples of time series: observations of temperature collected by a single weather station, so would have temperature over time. Pseudo-range observations collected by a standalone GPS receiver will have pseudo-range over time. Changes in refraction during the day, we're going to have refraction over time. Example of a spatial series: mean value of temperature for a network of weather stations, level height differences of a vertical network, anomaly of gravity for over a region. So in these three examples, what we have are values that represent certain phenomena spread over a geographical region. So, for example, we may have thermometers in each individual weather station, and so each individual measurements are basically a time series. But if you take the mean values of these observations and represent each mean value for each weather station for a day, that's then a spatial series. We may have the same thing. You can think of level height differences. So we may have the value of level heights for each segment of a vertical network. We may have the same with a anomaly of gravity over a region. So these are values that are represented having a 2D argument. Example of data series. So we have here a time series of GPS carrier phase single differences observed for two close by antennas. So what we have here is essentially the between antenna single difference. The vertical axis is in meters, representing the single differences. The horizontal axis is in seconds, starting at the beginning of the GPS session. If we look at this time series, we can ask the following questions. Is there a trend in the time series? The answer would be yes, there is a trend, and we could think that there is a linear trend. We can think also that there is another trend here that looks more like a sinusoid. In this trend, what is the signal? So if you're interested in a linear trend, the trend would be the straight line, the trend could be the signal, our signal, the quantity of interest would be the sinusoid. And what is the noise? Well, usually we consider the noise as the high frequency variations. And that's what happens mostly in geodesy and geomatics. And that's the basic assumption that we have in here. The understanding about signal in noise is very interesting because signal is essentially the information which we are interested in. And the noise is the information that we have no interest whatsoever. And typically, the interest may be different. So the noise of one investigator may be the signal of another, and vice versa. So signal and noise depends on what we are interested in. In time series analysis, our signal is typically the long-term variations. We can think of in terms of systematic trends. Okay, so the search for the signal constitutes the problem of data series analysis, and the search for the noise consists of the removal of systematic effects. Let me discuss a little bit more these two sentences. The search for the signal constitutes the problem of data series analysis, and the search for the noise consists of the removal of systematic errors. These two sentences imply that the signal, the information that we are interested in, is the long-term variations, and the noise are the short period variations. So we could look at it from a simple perspective like that. Let's suppose we have this time series, the zigzag time series. We clearly have a linear trend that we could fit as a straight line, and we have the zigzags. They would be now the high frequency variations. So this is our signal. Okay, this is our signal. This is the trend. And then what is the noise? Well, the noise is essentially the difference, every difference with respect to the trend. So we could then plot the noise. It would be something like that. These here, the search for the signal constitutes the problem of data series analysis. The search for the noise consists of removal of the systematic error. So when we have after remove the signal, what is left is the systematic noise, which is basically, in our case, is going to be the residual. The representation of observations in a data series, we are going to use the following notation. We're going to use L to represent the observations. Tau is going to be an argument that it represents either time or space in 1 dimension, 2 dimension, or 3 dimension typically. The subscript I represents a integer number, okay, which is basically the tag of observation. So, for example, in 1 dimension, tau may represent observation epoch or height. In 2 dimensions, tau may represent a pair of coordinates, like eastern and northern or lat and long, and in 3 dimension, tau may represent a triplet of coordinates, either the x, y, z coordinates, a Cartesian, geocentric, or latitude, longitude, and height of a point. We discussed the decomposition of observable before, but I think it's valuable just to refresh that. This is how we decompose the observation. The observation is composed by the true value, by a systematic component, and by the residuals. Okay, here the residuals. We can call the summation of the true value or the expected value and the systematic component by trend, and that's basically what we are looking for when we deal with the analysis of trend. So we are rewriting. Here we had before the observation. Let's put in with the argument equals to trend minus the residual. So from here we can get this expression. This is the trend. The trend is a difference between observation and the residual. Now, and as we have seen before, what the trend is nothing else but a variation, a systematic variation around the true value. The trend, therefore, can be seen as the deterministic component of the data series. So these would be the deterministic component. The residuals are going to be the random component. A previous knowledge or assumption of the analytical shape of the trend is required. What is done through the mathematical model. For example, we may either know beforehand or make an assumption that the trend is linear, quadratic, exponential, etc. The general form of the trend can take over a generalized polynomial, in which case we have the trend being equals to the summation of coefficients and base functions. So lambda 1 multiplying the value of phi 1, in this case here, usually phi 1, the first equals to 1, and then we have plus lambda 2, the second term, phi 1 plus lambda 3, phi 1 over 3, etc. Lambda n phi 1 of n observations. So phi are the base functions, lambda are the coefficients. Okay, the coefficients have to be estimated. The base functions will be selected based on the type of approach or the assumption we make about the shape of the trend. So if we consider n linear observation equations for u unknowns, and we can rearrange the expression for the trend in matrix form, in which we have here this matrix phi transpose following the argument multiplying lambda. Phi, matrix phi has a particular name. It is called the van der Monde matrix, which is composed of functional values of the functions. So normally the problem is ill-determined in the sense that n less than u. So it should be reformulated then. We add the residuals. Now we have u plus n unknowns. Choose a metric to minimize it with respect to lambda. The metric is the norm or the length of the residual vector. To get the least squares estimate, we minimize the quadratic norm. And that's what we have in here. Minimization of R transpose PR, because R, as we know, is given in here, T minus L. We can also replace the value of T that we have seen before, this is the trend, by its deterministic equation. So this is the minimization. What happens then? This is the minimization of the quadratic form written explicitly. How do we go for it? We compute the partial derivatives with respect to the unknown coefficients. After some developments, we arrive at this expression, which is nothing more than normal equations. Normal equations with a difference because we are not using the design matrix, we're using van der Monde matrix. The product of phi p phi transpose is known as the Graham's matrix. The Graham's matrix must be regular if you want to get a solution. We need G to be regular in order to get a solution for lambda, which is going to be G inverse phi PL.